Welcome back to the classroom. My name is Mr. Wong. In today's lesson, we're going to be looking at Module 5, Inquiry Question 1 of Projectile Motion. This is from the 2014 HSC Physics paper, and let's have a look at what it's asking and see how we can answer it. So we have cannonballs P and Q. They are fired so that they leave their barrels at the same height. You can see they reach the same maximum height after 3 seconds. Cannonball P is fired vertically upwards, while cannonball Q is fired at an angle as shown, as you can see here. So the question says, explain how the resulting motion of the cannonballs supports Galileo's analysis of projectile motion. The concept of independent motion and vertical components. Or should I say the independent motion between the vertical and horizontal components. So that's kind of what we're looking at here. So let's kind of explain how it works and then where to go from here. So we know from Galileo that his experiment showed if an object moves at a horizontal motion, so if it's moving at an angle, there will be an independent vertical component, vertical velocity, and a independent horizontal velocity. So that's what we can talk about here. He also mentioned that when we add this motion together, it's going to look pretty close to a parabola. So close to a parabola in terms of its overall motion. So it's going to dot like that. Okay. Now the reason why that is possible is because gravity is the only thing accelerating. So gravity is the only acceleration. And we also know that in the UX component, there is no air resistance, or at least that's the assumption, right? So that's the assumption that there is no air resistance. And so because we have one object or one side of the object that's moving at a constant speed, and then the other side where the speed is fluctuating, that's why we get a parabolic motion, okay? So that's what we can talk about. We also can say that the ball P and Q have the same vertical velocity. So although Q was fired at an angle, the vertical component of its velocity should be the exact same as the vertical component of this cannonball P. That's why they reached the same height at the same period of time. And again, it goes back to the fact because gravity is the only thing accelerating the two objects in the y component, so they both experience the same amount of acceleration. So hopefully that gives you a little rundown on what we could be talking about here. So let's have a look at our explanation. So we can firstly state that, the fact that Galileo stated that all projectile motions have an independent horizontal and vertical component. So Galileo states all projectile motion have an independent horizontal and vertical motion. So what we can say is the only acceleration that's experienced in the vertical motion is gravity. So gravity is the only acceleration experienced in the y component, or the y component, or you could say vertical component. What that means is at peak height, where both cannonballs have a final velocity of 0, they will drop, or they will fall to the bottom at the same time, or they'll fall to the bottom at the same time, and their velocities will increase at the same rate. Okay, so that's kind of what we can talk about here. There's a little bit more we can talk about. When I was writing the response, I had a little bit more space than I imagined writing on the tablet. So let's see what we can say. So we can also say, let's see. So we'll talk about cannonball Q on the side here. So as cannonball Q, Q is launched at an angle, its trajectory will look similar to a parabola due to Galileo's analysis of the independent motions. Okay, so what else can we talk about here? We know that the horizontal velocity is constant. So as this is because the horizontal velocity is constant, no air resistance, and its y motion, or its velocity in the y component changes due to the acceleration of gravity. So it might be a little bit more than you necessarily require, but this is kind of what we're trying to talk about. So here we explain how the resulting motion supports Galileo's analysis. We can see that they reach the peak height together because they have the same vertical velocity. So I can also write down both have the same uy component, okay, and they reach the peak height together at the same time. Therefore it means also the gravity, acceleration of gravity is constant, allowing them to reach the same peak height. So there's actually quite a few things we can talk about here. Okay, so we move to question B now, and it says the position of cannonball P is plotted at the 3rd, 4th, and 5th seconds of flight. The position of cannonball Q is plotted at the 3rd and 4th seconds of its flight. Let me just scroll out a little bit so you can sort of see where everything is. It says plot the positions of each ball at each second of the remainder of their flight. So whatever we can fill out here, and we need to show our relevant calculations. So we know that for the very first one, so ball Q, that one's quite easy to solve here because we know that Ux is constant no matter what. We know that the acceleration of gravity is a thing that applies to both of these spheres, so they will experience the same amount of displacement for the same amount of time passed. So you can see after a 1 second time lapse, they essentially drop the same number of blocks, okay? If I want to demonstrate where ball Q would be, it'll be somewhere along this vertical velocity here. The next question to ask is how far has it traveled horizontally? Now, in this block here, it shows that there are 3 blocks after this interval here. So the same thing applies for this one, our second ball here, and the next ball following. So we have our ball here, drops to this displacement. We go 1, 2, 3. That's where our ball Q would be after its 5th second. So the 6th second we therefore need to ask is, where does this ball fall? And we can use the formula S equals to UT plus half AT squared to help us solve the problem. So let's imagine the 3 blocks here. So that's 3 blocks. And we have a time pass of 1 second. Okay? We know that whilst this is being dropped, the horizontal displacement, initial vertical velocity is 0. So if we substitute that in, we have -3, so it's going down by 3, 0 plus half a, and then 1 squared for 1 second, okay? If we move the 2 over, that means it's 6 equals to a times 1 squared, which obviously just means a is equal to -6 units per second squared. Units being the blocks that we're referring to. Okay? So that's what we have there. You could cross-check that you have the right number of squares here as well. So if I did 2 seconds, so S equals to half -6, 2 squared, you'll find that the ball should have traveled 12 boxes. So if you look at that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Whoops, sorry, we start from 0 here. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so 12 dots there. So if I want to find the next one, the third time lapse, 3 squared, it should be about 27 boxes down. So we have 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So that's where it will be next. And therefore, our cannonball Q will be on the same vertical displacement, but it will have traveled 3 additional boxes to the right. So 1, 2, 3. And that's how you solve the problem. So the key method is just to understand when solving projectile motion, you do have to look at the horizontal motion and the vertical motion, as they are independent of each other. If you found this video useful in explaining how these exam problems can be solved, hit the like and subscribe button, and I will see you next time.